Hey, Luke. Good to see you. Today might be a teensy bit different than the last time. Sorry, I'm just... Yeah, right? I love this type of music. Yeah, man. Now let's go. There's a name for it. I really like it. Oh, I just moved. 1 second. I think we're set with that. We're set with that. Let's give it a try. Hello. Oh shoot! I am using the wrong avatar. 1 second. Let me need to go to the Sunday Morning Papers avatar. There we go. There we go. Excellent. Hello. Welcome to this edition of Sunday Morning Papers. Today we are back to the math grind. So what I've been trying to find is something that's a good introductory work through, such as it is, for path integration in the Wigner distribution. So let's see if I do this right. So if you see the math that's sitting on my desk there, that is a path integral. The goal is to use this for something specific that has to do with the Wigner space. We'll get into that. But I think I understand like the Wigner space. It's essentially a mathematical subspace where you can. It's just a way of representing things in certain terms, and it's useful for some mathematical constructions. So the goal is to try and understand the path integration piece of it because I have never done that before and I have no idea how to do it. So what I did is I downloaded 3 random papers of randomness to try and do a little, hopefully a little path integral introduction. So we might hop between the 3 of them. They're all kind of long, so we almost certainly won't get through this in the time frame for today. But we'll get part way through it, and then we'll save the rest for later. So that is the plan. If anything comes up where you have a question, I understand this is kind of, if you don't have a background in math or physics, this is sort of jumping in with both feet into the very deep end, and so I apologize. But if you have a specific question, if you would like me to cover something more in depth, let me know. And if I don't understand it, which there's a very distinct possibility, we'll try and work through it and understand it together. So, with that said, let's bring our paper back. Okay. So, um, the path integral and the Wigner distribution are both used in quantum mechanics, right? So that's the physics of very small things, and things get nice and weird, and you get things in multiple places at the same time, and things act like a wave instead of a particle, and yada yada yada. I don't know how much background you might have in quantum mechanics, but quantum mechanics is weird. Anyway, the big thing that makes quantum mechanics weird is rather than dealing with things like a ball flying through the air in classical mechanics, right, where you have these things that are at a specific point moving with a specific momentum, it treats things as waves. And if you think even of a water wave, right, traveling through a pond, it's not nice and localized in the same way, right? So even if you have multiple water waves that are occurring together, like you did this and this and this, and say in this spot where you've got these two waves kind of superimposed on each other and they're adding, it's still not very localized, and this will move off, right? As this wavefront moves and this front moves, you get things moving around. Anyway, things end up being weird. It's less weird when you understand that it's just wave mechanics, right? It's just what waves do. Waves are weird. Um, the weirdness in quantum is that you're applying that to things that you typically think of as being particles, right? Individual objects that have a specific location, like known precise location, momentum, all that stuff, right? And in quantum mechanics, you don't treat things that way, so it gets hence weird. All right. So quantum interference, which is, again, since everything is a wave, we're doing a little background, but since everything is wave, interference is when two waves add together, right? So if I have this wave and this wave, right? When they encounter each other, they'll add together. So if I do a little plus there, it'll be a bigger wave, right? The amplitudes add. Um, yeah, no worries, no worries. I'm just going to try and explain things as I go through. If something tickles you as interesting that you'd like to see more of, we can talk about it either here off stream or on another stream. Um, you don't have to know all the calculus. I will try to explain concepts and how these connect, but feel free to lurk. And like I said, if something bothers you or tickles you or makes you interested in some way, feel free to contact me during or after stream some other time. We can go over plenty of things, so don't worry about it at all. Um, right. So the other thing that waves can do is if I have a wave that's doing this, and then I have a wave that's opposite as doing this, right? So it's going down when this one's going up. If we add these together, they will cancel each other out, right? So that is the interference, right? When the waves are opposed to each other, they'll cancel out to zero. When they are exactly in phase with each other, right? So when they go up, maximize at the same time and minimize at the same time, they double, they add together. And then if you shift one with respect to the other, right, everything in between, right? These are just obviously the two extremes. So again, with quantum mechanics says that, well, particles also do this, not just, particles act in with wave-like behavior. And so particles can interfere with each other and do all these sorts of weird things. Yeah. Thank you. So quantum interference and exchange statistical effects can affect the momentum distribution of functions, making them non-Maxwellian. Oof, there's a lot under there. Statistical effects can change the distribution of how things are. That would be a whole thing in itself to go through that. So don't worry about that. Such effects may be important in the studies of kinetic properties of matter, so how matter moves, right, through space. Can I make it bigger? We can try. Let's see. Um, view. Zoom in. Let's go to 125. And now if we do this again, is that a little better? Is that more visible? Um, no? Okay. Shoot. All right. Let's try it again. Okay. View. Zoom to 100. Oh boy. That's a little bigger. uh, so my one fear with doing things this way is that even on my tablet, I have to scroll back and forth. Let's see. That's the best way to do this. If I switch, okay, hold on. Uh, Minor technical messing bouts. Let's see. No. What if we rotate our tablet to landscape? Okay. Eve. Alright, so if we do this, might be a little bit better. Give me 1 second, just look at this. Okay, that I'm able to fit everything. So now I can just change. Well, it wasn't um the way I had it set up in OBS with Baron in the background. It was the physical size of my tablet being able to have it on there. However, let's see here. So, if we do this, sorry, 1 sec, just looking at how this is gonna look. If I go down here, all right, what's the width that needs? All right, it's about this width, and then I can at least have that. Okay. Can I just a tidbit, just a tidbit. There we go. Okay, I think that's better. If we do this, and now if we take Baron, we'll move Baron over here. I'll just have to remember that he's in the bottom right there. How about something like that? All right. So that's more visible. Okay, so I'll just have to remember that Baron's on the bottom right there. Okay. Anyway, we're gonna let's just start cranking through this paper and see what we can find. All right. So introduction: computer simulations is one of the main tools in studies of thermodynamic properties of many particles strongly coupled systems under extreme conditions. So if I want to know how, oh, my coffee's gone. Fortunately, half my coffee spilled on the carpet, but that's fine. If I want to know how, say, a bunch of particles is going to function, I'm going to actually move Baron to the other side over here. Here we go. Yeah, but he can yell to his heart's content. Outstanding. Okay. If I want to know how, say, a bunch of ions are operating under extreme heat, right? Oops, I forgot to transition. There we go. It's actually very difficult for me to make a lot of these simulations either because the conditions are too extreme or because it's impossible to keep track of all the things that are going on. Um, and so you can't really set these up experimentally. And so, or it's very, very difficult and expensive more often to set it up experimentally. So, computer simulations are one way that you apply these things, right? Some of the most powerful numerical methods for simulation of quantum systems are Monte Carlo, based on path integral formulation of quantum mechanics. So a Monte Carlo method, um, you could think of it like this. If I have, I'll give you an example from something I'm doing, right? Um, I have a single set of data that I'm looking at, right? And I need to chunk this up. So part of it is my training data that I use to set up my model, right? And part of it is my validation data to see if the model's working. And so what I'll do is I'll randomly select some percentage of the overall data to be training and some to be the validation. Here's the problem. What if, because of the random setup I happen to use, um, there's something in the validation data or something in the training data that isn't random, right? There might be some other effect that's going on, or um, I might just get different results when I compare these two. Once I make my model and compare it to my validation data, depending which validation data I choose, I might get different results, right? There's different outputs to the model based on the different data. So how do I say coherently what this model is actually doing? Well, what I can do is I can run a whole bunch of these different things, right? I can randomly pick my validation data a whole bunch of different times. And each time, because it's random, my validation data will be different. And then I can statistically look at, all right, what's the outcome of all of these together? What's my median outcome? What's my standard deviation of my outcomes? And then I can start talking about something more coherently that's not dependent on the specifics of how I randomly selected this specific set of validation data and this specific set of training data. It kind of runs through all those possibilities and evens out a lot of the noise effects that you would see run to run, right? So that's a Monte Carlo method. You're using you're uncovering the underlying statistics by doing a lot of different runs, a lot of different random runs, and when you do that, you can see the statistics are kind of going on in the background. And the path integral formulation is what we're trying to figure out. These methods use path integral representation for partition function and thermodynamic values, such as the average energy, pressure, heat capacity, etc. Right? So these are different properties of a gas, right? If you have a gas, the partition function is going to kind of tell you what states are available for that gas, right? Because each of the particles in a gas can have a velocity, can have a momentum rather. It could have a position, right? They could exchange all these things. They could be in different places. They could be going in different directions. And so there's this huge set of possible states that this gas can be in. And so the partition function is representing this enormous set of states where that takes into account how all the different particles could possibly be, right? You can't actually count where all the particles are or the different states that all the particles are in because the numbers are huge, like astronomically huge. But what you can do is you can start dealing with them as a group, and this is where it becomes statistical physics, right? Thermodynamic physics is often statistical mechanics. It becomes statistical because you don't actually care about particle number 3,471 and how it's precisely moving, even though theoretically, if you want to know what's going on, you need to know all the momentum and all the positions of all the particles and take them all into account. But you can't do that. Functionally, it's impossible. So what you do is you look at the overarching statistics and invent these sort of statistical concepts like temperature. right? Temperature is the average, it's the mean kinetic energy. It's a representation of the mean kinetic energy of of the particles that make up something, right? Temperature is not a property of the individual components of a gas. It is a property of the gas as a whole, right? So it's a statistical property. Um, right. So same thing with pressure, right? Pressure has to do with the momentum of particles bouncing off the so momentum transfer from particles hitting the edge of whatever enclosure they're in. Sorry, let me move this over so it's visible, or I'll just do it over here. Let's see. Yeah, so you have a bunch of particles and they're bouncing off. Well, every time the particle hits, right, you get the momentum transfer, and this whole set of momentum transfers is the pressure, right? You're not tracking each individual particle. You're looking at them, all the particles as a whole. Um, okay, PIMC methods. So that's the path integral formulation. Are widely used for studying dense hydrogen plasma. So something like at the center of a star, electron gas in metal. So electrons moving through a metal can kind of act like a gas, right? They're able to freely move similarly to a two-dimensional gas. You can kind of think it's an analogy. So it's called an electron gas. It's not a precise analogy, but it's what it's called. Electron hole plasma. So that's where you have an atom that's missing an electron will come and pair, like an electron will come from this atom and move into the empty spot in the energy level of this atom, and now there's a hole in this one. So it looks like a positive charge went this way and a negative charge went this way. So that's the electron hole pair. This is very important in solid state physics, specifically on with solid state electronics. So on the border of your PN junction, this is what's going on in a what are they called? Like in a transistor junction, right? In your computer where you have silicon. Why do you have silicon as your computer? It's a doped metal, so you end up with this area where you have lots of excess electrons. You have an area where you have, right, so this is a negative charge, this is a positive charge area, and then you can have some electron flow between the two to even out in this border region, and it's called a PN junction. And depending on how you bias this, it either blocks or allows current to go through. So that's how you get your transistor 1-0 switch. So electron hole plasma, let's deal with that. In semiconductors, right? That's what I was just saying. Don't do that. Superfluidity. This is a quantum property of very, very, very cold fluids, where they'll act kind of like a single quantum state. And they'll do weird quantum mechanical things like tunnel their way out of their container and do kind of weird stuff, flow upwards, all kinds of crazy things. And even quark gluon plasmas. So that's extremely, extremely, extremely hot plasmas, like early universe type plasmas before things like protons and neutrons had the ability to condense. Unfortunately, PIMC methods cannot cope with the problem of calculation of average values of arbitrary quantum operators in phase space or momentum distribution functions. In other words, path integration is, you're talking about specifics and the possible set of how a specific particle moves. It's not an average, it's not a statistical um calculation, right? Um well, this problem may be central in studies of kinetic properties of matter. Well, all right. So what they're saying is PIMC methods are not good for averages for these statistical kind of calculations. Um, but these problems are central in studies of kinetic properties of matter, right? So you have this formulation that's useful for some things, but isn't useful for these statistical things. But these statistical methods are very important for this type of thing, right? So this is kind of building up the reason why they're doing this paper, right? Quantum effects may strongly disturb the momentum of Maxwellian distribution functions and are important in the study of kinetic properties of matter at low temperatures and under extreme conditions, where particles are strongly coupled and have perturbative methods cannot be applied. So, what they're saying here is quantum effects can. So, if you're Maxwellian distribution is kind of like a normal distribution, right? So if you're looking at the statistics of something, typically you'll see this normal distribution, it's called. Um, and you could say that certain, right? So if you're looking at heights in a population, right? Uh, Here is your average height, right? That's where most of it is. And then this might be one standard deviation and, what is it? 70.07% will be within one standard deviation. I think it's 0.707%. So 70, yeah. 0.707 is within one standard deviation. And, it's the normal distribution. You see this all over the place in mathematics and physics. It's just kind of the classical distribution you'll see when you're looking at the statistics of randomly distributed particles. There's a similar distribution called a Maxwellian distribution that pops up in quantum mechanics, kind of like if you have an undisturbed setup, right? This is completely random, undisturbed. But now if you add some influence to it, now all of a sudden your property might look something like this, right? Where you have a shorter tail on this end and a longer tail on this end, right? Because now I'm not dealing with purely random processes. I'm dealing with proper processes where I've given it a push. And so that's what it's saying, is that some of the quantum effects that go on can disturb the normal random distribution that you'd expect to see. And are important to studies of kinetic properties of matter at low temperatures. So how particles move around at extremely low temperatures and under extreme conditions, so extremely high pressures, temperatures, that kind of thing, where particles are strongly coupled. So they're kind of acting as one. They're not acting independently anymore. So you can't just look at this random statistics and say, all right, what is it? It should look something like this. No, it doesn't look like this anymore, because now everything is not independent and random. They're all tied together and they're all interacting with each other. And so you can't apply the normal statistics to it. Okay. The mentioned before PIMC methods, or even recently developed configuration path integral Monte Carlo approach, we'll have to look that one up. That could be useful for something. Anyway, up to now cannot solve this, cannot also solve the kinetic problem, right? So it's useful for some things, but it's not able to solve the kinetic problem under these sorts of weird conditions, what he's saying, right? So again, this is all building up justification for why they're writing this paper. The Wigner formulation of quantum mechanics in phase space allows more natural considering not only of kinetics, but of thermodynamic problems. So what's a phase space? Well, if I'm looking at a particle in real space, right? I'm going to have 3 dimensions, right? It'll be X, Y, Z here, right? And I have a particle. Let's do a little, right? Here's my particle, and it's moving off in this random direction. Okay. It's got a position and a momentum in XYZ space, right? Um, what happens if I have a whole bunch of these particles and now I'm like, all right, look, I can't keep track, right? This is all filling up with particles going in different directions, doing different things, and it's going very confusing. I'm like, all right, I need to look at this differently. And this is something you'll quite often do in physics. You're like, okay, all right, there are too many particles. I need to look at this a little differently. Instead of plotting an XYZ plane, what I'm going to do is I'm going to say, all right, I'm going to ask for how far from zero, in other words, how far am I from the center of my plot from 0, 0, 0? And then on this axis, I'm going to plot momentum, right? The magnitude of my momentum. And now I could say, all right, well, this particle is this far from zero and it has a momentum of this. And this particle is this far from zero and it has momentum of this. And this one is like this. And I can, oh, look, I've got like this line here. Now I can say something concrete about these particles as a whole, right? What I've done is I've built a phase space, right? It's a space that's not physical like XYZ physical space. Is I've plotted them in a different type of way, right? I'm looking at their distance from the central point, and I'm looking at their momentum, right? This is how you try and take different attributes of the particles and you look at them in different ways, right? And then you could, there are ways that you can do a mapping back and forth. When I say distance to zero, right? How do I find distance from zero? Well, it's the square root. Oh, sorry, that was really bad. Let me try that one again. Right. Um, D is going to be the square root of x squared plus y squared plus z squared. Oops. So now I can map from any position here into my location here by using this formula. So you can go back, you start being able to build these mathematical constructions where you can go back and forth between these different phase spaces. And they're useful for different sorts of things. It's words. It's just different ways of looking at the properties of the particles to give yourself understanding as to how they're interacting in different ways. Right? So that's what's going on. Right. Okay. Method for phase space treatment of single particle quantum dynamics and Wigner approach in microcanonical ensembles were proposed in all of these. Right. So in other words, this Wigner distribution is a way that you can talk about individual sort of single one-off particles. Recently, a generalization of the one-body Wigner Monte Carlo methods to many-body distinguishable particles has been done. So again, now you're not just talking about single particle, you're talking about a lot of particles. Also, they're when when he says they're distinguishable, that means you have to keep track of each one individually. You can't just say, they're pretty much the same thing, right? If you look at a bunch of electrons, they're literally identical. The only thing that's different between the electrons is if they're all at the same energy level, right? The only thing that's different is their location momentum. But they're interchangeable. If one takes the spot of the other, like if two of them switch spots, it is completely indistinguishable. Distinguishable particles means that you have to keep track of, right? If A and B switch spots, you still have to keep track that it's now BA is your ordering, right? It's not AB, it's BA. You can't just say, well, this one's now A and this one's now B because you can't tell them apart anyway. So that's what it means by distinguishable. Wigner dynamics of relativistic particles was studied in 21. However, for theoretical studies of kinetic properties, the ab initio many particle approaches in phase space are required. Ab initio from I think it's from the ground. I think from the beginning, right? You have to restart. I think is what ab initio is is saying. So in other words, you have to start from the ground up if you're going to talk about kinetic properties of particles in this Wigner distribution space, you got to start from the ground up. You can't, we have to take a look and see if we can start putting something together. This paper, we continue to develop the ab initio path integral Monte Carlo approach in phase space by using the basic idea suggested before in number 22. So in this other reference, here we have generalized the path integral representation for Wigner function to three-dimensional many-particle quantum system with Boltzmann and Fermi statistics. There are two types of statistics that operate in particles. If you talk about thermodynamics, one of them has to deal with if the particles can stack on each other, and one of them has to deal with if they can't. So, for example, fermions. I'm gonna get this switched. Bosons. You can't have two bosons with the same properties in the same space. Fermions, you can, right? So fermions might be something like a photon. A boson would be something like an electron, right? You can't have two electrons in the same space at the same time with the same spin, right? There's an exclusion principle that happens. So those result in different statistics and different properties. And so that's what he's talking about, the two different major categories of particles. Here we present also alternative single momentum approach for calculations of momentum distributions and quantum observables. So those are things that you can actually measure in a quantum system, right? There's a lot of stuff in the quantum system that you can't directly measure. This approach allows avoiding harmonic approximations, right? So you can kind of approximate things as harmonic oscillators and do a bunch of math on it and try and say, yeah, it's close enough. But they don't have to deal with that. At consideration of degenerate systems or interaction fermions, partially overcoming the well-known sign problem for degenerate Fermi problems. I don't know what that is off the top of my head. These two methods were tested in one sample of models, in some simple models like particles and external potential field and ideal Fermi gas. So what he's saying is, hey, look, the prior methods of attacking this, or the prior methods of setting up these sorts of problems using the Wigner distribution and the path integration have run into issues. Our approach doesn't run into these issues. That's what he's saying. Right. That is what he is saying. Okay, so the Wigner function in canonical ensemble. Average value of arbitrary quantum operator A can be written as a Weyl symbol A of PQ average over. I'm just going to read this and then I'll try and understand it and break it down as I'm trying to understand it. So give me a second. Average over phase space with Wigner distribution W of PQ beta V. So the expectation value of A, right, is the integral over all particles of momentum and position. Actually, 3 times. Oh, okay, yeah, because all are particle space, right? I think n is yes. And here's A as a function of momentum and location, and W is the Wigner function, which let's look up. Hold on. Give me a second. I want to write down what the Wigner function is. I believe we ran into this in some other papers, but I would like to actually grab that and write that down here. So let's see. We want Wigner function of PQ beta V. Okay, Wigner quadratic distribution. Okay. Wikipedia, are you gonna save us? Sometimes Wikipedia is really good for this kind of thing. XP, right? Symmetric and sorry, 1 second. Just looking up versions of this. Okay, that's that. I know what that is, but what is the 4-dimensional Wigner function? Huh? Huh? Why are you not telling me this? Why? Wigner file transform and phase space formulation. Ooh, phase space formulation. Here we go. Is it that and the information the vial transformation? Okay. Okay. The Wigner original transform non von Neumann evolution equation. Sorry, I'm trying to read this real fast, see if I can get it. Okay. No, that's the Hamiltonian. That's not what I want. That's not what I want. That's not what I want. Regular evolution. Okay. Classical limit. Blah blah blah. Blah blah blah. Blah 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 blah. That's not what I want. That's not what I want either. You're not anything close to what I want. Okay. Was it probability distribution? I apologize. I'm just trying to look. Yeah, that's X and P. Okay, I understand that it's that for X and P. Okay. I am only finding the 2-dimensional version of this, which is kind of irritating. Okay. Properties. Reversal operator. No. State overlap. No, it's still 2-dimensional. Yep, phase space, that's that. Okay, we're not sure that. Okay, yep, Jacobian, yep. Yes, we have lots of those kinds of things. Fourier transform of the Wigner, yes. Fourier transform, Fourier transform of W. Oh, jeez. Okay. Well, interesting. So what I was trying to figure out is what this 4-dimensional Wigner distribution is, right? We can write down the 2-dimensional Wigner distribution. I think that's supposed to be dq. Okay. Dy. All right. Okay. So. All right. Okay. So let's talk about this for a second. Okay. First off, let's talk about the variables. Right. P is momentum. It usually is. Q is position. All right. Typically V is volume. Sure. Beta is potential, I think, in this case. I'm not really sure. Hold on. Let's see if he says in a second. Let me just scroll down and see if he explains what beta is. Beta is 1 over KT. Okay. d of beta v is the partition function. Okay, so that's what it is. All right. So, okay. So here's what we're talking about. Here's what we're talking about. Got it. Got it. Got it. Got it. Got it. Okay. Let me describe this a little bit, at least. And while none of us, including myself, will have a full understanding of what's going on here, because I am not a quantum mechanics person, but maybe we can understand a little bit. Okay. P and Q are momentum and position. Beta is 1 over kT, where K is Boltzmann's constant, right? So beta is your stand-in for temperature. V is volume, right? So what this is talking about is kind of a 4-dimensional space. Or you can think of it as, you could talk about a 2-dimensional slice of it, which is, what is my P and Q setup for a given temperature and volume, for example, right? That's what's going to be. Now. So let's see. That's as a function of that. Hold on one. I want to see if I can find one. P, no. Can I find the Wigner distribution of P and Q, not X and P? P and Q. Wigner distribution of P. Mm-hmm. Mm-hmm. Right, so the wave function is okay. Alright, okay, so that's that. Vigor distribution, XP, XP. Okay. But why is it x plus y? What is psi of x plus y? The slope of psi of x. This is not helping. Okay. Maybe in here it'll do. Okay, here we go. Here we go. Here we go. I found it. I found it. Q minus y. Okay. 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 So here is. Let's see. Make sure this visible here. W of P and Q. Is this as small as it goes? It's not as small as it goes. Okay. So what is the Wigner distribution of momentum and position for a quantum system? It's really for any system, but in this case for a quantum system. I'm going to take the integral from negative infinity to infinity. Actually, hold on. There's a normalization. I forgot the normalization constant already. And I'm doing well here. Okay. Normalization constant is 1 over pi h bar, right? So pi is obviously the constant pi. H bar is h over 2 pi. It's the Heisenberg, not Heisenberg, freaking constant. Why am I forgetting the name of the constant? Anyway, it's named after one of the physicists, but it's a constant. Don't worry about it. So that's just a constant number out there. That's a normalization essentially. And then we're going to integrate from negative infinity to infinity, right? So we're integrating over all space of psi star q plus y psi. I'll explain psi star psi in a second. q minus y times e to the 2i py over h bar. All right, this is the Wigner distribution right here. So what are we actually doing in this? All right. Psi is our wave function, right? It's psi of q. Q is a summation of XYZ, right? So it's psi of position, right? And it's gonna be for a particle, right? It'll be some wave like property, right? To turn that wave function of a particle into a measured particle, what you do is, to turn that into an actual real probability, you have to multiply it by its complex conjugate, which is what the star is. So, the complex conjugate, you take any complex number and you just turn I into negative I. That's all you do. You just switch the sign. I goes to negative I. When you do that, the imaginary portions of it, when you multiply them together, will drop out. So that's why it's called the conjugate, right? When you multiply it by its conjugate, you end up with a real output, real numbered output. So we are integrating psi star psi, which is kind of what you would normally do to find the position of a particle. But in dy. But in this case, we have something else going on, right? We have this y term. So now I'm looking at psi star is shifted in one direction and psi is shifted in the other direction. And then what I'm integrating over is these shifts, right? So what I'm looking at is, let's imagine, just to make things easier, right? We're going to say psi equals 2x. It's not actually a real thing, but we're just going to say psi equals 2x. Hi, Gothic. So we're just going to say psi is 2x. Cool, right? Actually, we need to make it complex. So e to the 2 pi I f, right? So there we have our I. There's our negative. Well, I hope you are enjoying yourself as I scramble my way through all of this shenanigans. Anyway, so psi is going to be some wave function, right? So here's your wave portion. Here's your position, right? It's just 2x. So psi star, by the definition I've given you before, what's psi star? Well, it's 2x times e to the 2 pi negative I times f. Literally, just that's all I've done is I replaced I with negative I. Cool. Then we've done our complex conjugate. Easy. That's the easy part. Now we're saying, okay, we want x now becomes x plus y, right? That's our plus y. And in regular psi, it becomes x minus y, right? So now I can imagine y. Let's pick a number for y. Let's say 2. Y is 2, right? If y is 2, then I've got psi star psi now becomes 2 times x minus 2 times 2 times x plus 2 times 1. Actually, when you multiply these two together, they drop to 1. That's why they're complex conjugates. So you end up with this, right? Which I can say is 4x squared minus 4, right? 4 times x squared minus 4. Did I do that right? Yeah. There we go. right? That's for y equals 2. But y could be any number, right? And I'm taking the integral is literally just adding up all the possible numbers. So what I'm doing is I'm taking this 2 number and I'm saying it could be anything, and I'm going to add up the results of doing it across all of these possible numbers. That's what I'm integrating, right? So I still end up with a function of f, right? If you notice, this is still a function or a function of x. So I still end up with a function at the end of it. I haven't gotten rid of all my variables, but what I've done is I've gotten rid of my y variable, right? This is what the Wigner distribution is, right? It's integrating over y, and so ends up as a function of momentum and position, p and q. Again, remember, q can be an xyz position, right? So in this case, y is also an XYZ position, but it's like all possible XYZ positions, right? It's just a dummy variable. I'm integrating it out. It doesn't end up in my final thing. I'm just saying this is some dummy variable I'm throwing in here as a placeholder, and I'm taking all possible values of it and adding up all the results. That's essentially what it's doing. Right, so that's W. Right, that's my distribution here. And again, to take another step forward, this is a 2-dimensional slice of a 4-dimensional W. So this is a W with a static beta and V, right? This is, I have chosen a specific temperature, I've chosen a specific volume, and then within that temperature and volume, I'm going to end up with this W distribution, right? Then I can shift my temperature or my volume and end up with a different P and Q distribution, right? So it's a 4-dimensional space. In this case, I'm looking at a 2-dimensional slice of it. This is one of the benefits of a phase space. Even though it gets really confusing, you can start accounting for more than just position and momentum, right? You can start accounting for all these different variables because the math is all the same, right? The math doesn't care what variable you're talking about. So you can talk about 100 variable phase space, right? It could be 100 dimensional phase space. It doesn't really matter. It could be an infinite dimensional phase space. It doesn't matter. The math is all the same. So I can start taking into account all of these different disparate variables, as long as I do it correctly, within one distribution, and I can start doing math on all of these different properties of my particles at once. And I could get information about my system as a whole, right? That's ultimately what its use case is. This is why phase spaces are useful. Because you can look at things like this. This is a single phase space of position, right? One variable is position, one variable is momentum, one is position, one is temperature, and one's volume, right? These are very different variables, but they're all together in the same phase space because I'm using a phase space. That's the benefit of this, right? Okay. All right, but we're also talking about this other variable, A, right? And A, okay. So A is some operator. It doesn't matter, right? It's an arbitrary quantum operator, so it could be the Hamiltonian, it could be whatever. It doesn't matter. It's just some operator. So an operator is something like, it could be a derivative, could be an operator, right? It's literally doing some sort of operation. You might be doing an operation that's pulling the momentum out of a particle distribution. It could be any of a number of different things, right? We don't care what that operator specifically is. So it's some operator, a hat. That's a function, again, of momentum and position. Oh, one other thing I want to say before we hop down. Right, so we're integrating here. We're saying that the average value, we're trying to find out what the average value, say this A operator is pulling out the momentum, the average momentum of my set of particles, right? That might be what it's doing. It's just the result, A just gives me the momentum. That's it. That's all A does. If I want to know the average over a whole lot of different particles, what I do is I do this operation, right, where I have my Wigner distribution. My Wigner distribution is telling me how the particles' momentum, position, temperature, and velocity distribution is, right? It's giving me all that information. A is operating to give me the actual momentum piece of it, right? That's what A is doing in here in this integral. And then when I integrate over all spaces, then I'm going to end up with the average value of A, which is this icon here, right? It's the bracket A hat, right? So the average value of momentum is this operation. What am I doing? I'm integrating. So again, I am taking over all these possible variables. How many different variables are there? This is where this will show you the problem with trying to do a standard approach in statistical mechanics, right? How many variables are there? Well, there's 3n position variables, 3n momentum variables. I did that backwards again, right? So what does that actually mean? 3n position, 3n momentum variables. Well, each particle, let's say I have 10 particles, right? Each particle has an XYZ position, and each particle has an XYZ momentum, right? So, right, because it can be momentum is just the mass times velocity in a specific direction, right? So I can have momentum moving in the X direction. I can have momentum moving in the Y direction. I can have momentum moving in the Z direction. And I have its location in XYZ space, right? 3 particles in a 3-dimensional space moving in a 3-dimensional direction. So it's got an XYZ location and an XYZ momentum. But each particle has that. So if I want to know what's happening in all possible particles, I have all of the x's, right? Let's say I have n particles, right? Let's say I have n equals 5, right? So then I'll have 5 x's I have to account for, 5 y's I have to account for, 5 z's I have to account for, and 5 px's I have to account for, 5 py's I have to account for, and 5 pz's I have to account for. All of a sudden, I have 5 to the 6 different possible dimensions that I have to integrate over. Right? I have to account for all of these different possibilities if I'm going to actively say exactly what's going on with all of these 5 particles. And you can see if you have, I don't know, 10 to the 50 particles in a room, how this quickly gets out of hand. The number of dimensions that you have to deal with very quickly gets out of hand, right? This is why you transition from trying to trace individual particles into talking about things like pressure and temperature, which is the average values of all of these, like integrated over all the possibilities, right? This is exactly what this is getting at, right? This is how you get statistical mechanics, thermal physics, is you say, all right, we're going to derive exactly what temperature is, what pressure is, and so there are a few other statistical properties, right? We're going to derive it from the individual movement of the particles and then scaling up that movement to the point where it's way out of hand, right? So that's kind of what we're looking at here. We're looking at the average value. We are integrating over all possible position dimensions. I'm sorry, momentum dimensions, all possible position dimensions. This 2 pi h bar 3 to the n is the normalization constant. So again, this is just a constant that came from we saw before. The A is our our operator, right? This is our operator in the vial distribution, and this is the vial distribution itself. Okay. Where the vial operator A is, let me see. DS. Okay. So for A, right? A as a function of this initial operator is just doing the same thing we did for psi, where we're going over negative y to positive y. We're doing the same thing here, right? Negative, only we're calling it s. Doesn't really matter. Again, it's still a dummy variable. We're integrating over it. The variable doesn't end up in our final function. The variable goes away because we're integrating over all of it. And so we're going over, if you notice, there's 3 NS's, right? Because we have an S for each of these different particles times 3. And we're doing that, and this is the inner product, which is functionally identical to this. Okay. So what we've done is we've taken a transform, really. We've transformed this operator A into vial, the Wigner distribution space is what we've done. Really, this is similar to a Fourier transform, but in this case, it's moving into a different space, right? It's not moving into Fourier space; it's moving into the Wigner space. So, okay, cool. Sorry, I'm just scrolling down to see where we're at because we're already over an hour into this, and I have a lot of work to do today. So, I know we're going really slow, but I think I am going to stop here for today just because I've got other stuff going on that has to get done today. But the point being, this is where we've started to have a rubber meeting road here in this section. And this is what we have to start understanding, these basics. I do not fully understand this. I sort of have I have hints of what's going on based on other stuff I've done, but I'm not, I don't fully grasp this either. Right? This is some very complicated stuff. No, don't cry in the gym. How much longer do you have in the gym? How much longer is your workout? I couldn't bear to be the cause of you crying in the gym. Then you're gonna like not pay attention to what you're doing. You're gonna drop the bar on your toe. I couldn't bear it. Okay, fine. We'll keep going a little bit more. All right. Tell you what, Gothic. Let me know when you're gonna go in the sauna, and then we'll cut it off after that. Just for you, Gothic. Just for you. Okay. So, what I was gonna say is next time we do this, when we come back to it next Sunday, we will go through this again, because what I have found, at least for myself, is I have to go through things 5 times to sort of understand them. And so I'm starting to scratch the surface myself. Hopefully I'm starting to scratch the surface with you guys as well. But there's a lot of digging that we have to do. Anyway, but I'm going to keep going for now. Okay. The vial symbols for common operators like P, which is the momentum operator, Q is a position operator, P squared is momentum squared, Q squared is position squared. H is the Hamiltonian, which is let me make sure I get the right one. It is the kinetic plus the potential energy of a system, right? Is a Hamiltonian of it. The Lagrangian is the kinetic minus the potential. It's a very important formulation. No, 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 no. Of course not. I'm gonna keep going. Okay. So H is Ke plus Pe. That's the Hamiltonian. Uh, there's a whole, and the Lagrangian is Ke minus Pe, right? Um, each of these has a whole. You can build an entire set of kinetics. Oops, let me scroll over so you can see what I'm doing over here. Each of these has a whole formulation of kinetics based around them. You can formulate all of your kinetics, and then as a result of your kinetics, your quantum mechanics and your other stuff around a Hamiltonian, you could formulate it all around Lagrangians, right? So anyway, quantum mechanics, typically you'll see H, you'll see the Hamiltonian. Okay, etc. can be easily calculated directly from the definition of 2. So again, A is an arbitrary operator, so you can plug any of these operators into it. What is the ultimate purpose of mathematical process in non-math terms? So, what we're trying to do is we are trying to describe how, what the state is of, okay, all right. When we apply an operator in quantum mechanics, we are trying to find some information about a system, right? That system might be a single particle, right? Which has a function psi of pq, right? It's got a momentum and position, right? This is a quantum particle, and I want to know what the momentum specifically is of this quantum particle, right? What I would do is I would end up doing psi p psi, right? This inner particle with this operator in the middle is going to give me my momentum value at the end, right? So these operators, what they represent are different observables about the particle. When you perform this, so in quantum mechanics, when they talk about measurement, what they're talking about are these kinds of things, right? The position, the momentum, the energy, which is the representation, right? The Hamiltonian is just telling you what the energy is of a system, right? These are things you can directly measure. You cannot directly measure psi. You can directly measure P, right? You can measure the momentum. And if you did this over a whole bunch of, right, this is going to actually give you the average P, right? The expectation value of P. So if you did this over a whole bunch of times, you'll end up with a distribution of P, whatever that might be. Usually it's that Maxwellian distribution. But so the point is, we are taking this operation in quantum mechanics, right? You take an operator, you operate on some system, and you get a measurable result, right? This is what a measurement consists of mathematically, right? This is the mathematical structure of a measurement, but also the mathematical structure of many different interactions within quantum mechanics. It's not just a measurement. Anyway, so that's what these operators are. And so what we're saying is, all right, instead of looking at stuff in standard XYZ momentum space, I want to look at stuff in this other phase space called the Wigner space, right? And it has other properties. It's able to describe different aspects of my system in different ways that makes it easier or harder to apply mathematics to, right? This is the reason why I'm going into this, and I've talked about this to those who have been in prior ones, right? There is a mapping between W and my Fourier space, but I can describe a little bit more succinctly using Fourier what this is and why we care about it. All right. So let's say I have some, again, using my background with, oops, can't quite see that. All right. Using my background with, radar engineering, right? I have some radio signal. And that radio signal looks like this and looks like this and has all these properties to it, right? So if what is this actually? This is literally voltage over time. So if I measure the voltage at my antenna at some specific time, I'm going to get this measurement, right? And if I do this a bunch of times and I look at what it is, right, I get all of these voltage measurements. Great. Cool. This is my signal in time. It's a little difficult to tell what's going on. I could obviously give certain information about what this looks like, right? I could look at these spikes in time and that kind of thing. But there's other information that's going on in this signal. For example, what are my frequencies that are here, right? Let's say I'm talking about something like an amplitude modulated signal. What is an amplitude modulated signal? So I'm going to have something that looks, and forgive my drawing, it's not going to be very good, but looks kind of like this. Right? What's going on here? This up here, this like little squiggles, those little squiggles are the information that I put on my signal. This is the audio or the data or whatever it is I have. This is the amplitude modulations that represents the audio on my signal. This big thing here is the carrier frequency that's literally carrying the information on the audio signal, right? If I want to find this audio signal, I need to tune into this carrier frequency so that my antenna is collecting this carrier frequency. And from there, I can deconstruct the audio signal, turn it back into audio, and play it through my radio, right? In order to do that, I have to know what these frequencies are. How do I know what the frequencies are? Well, I could do something called the Fourier transform, which goes from voltage time space, right? That's what this is. This is voltage time space that I'm looking at. I'm looking at different voltages at different times, and I'm transforming it into voltage frequency space. So I'm not looking at time. Instead, I'm looking at how many. All right. So I have this big low frequency signal, right? So that's going to be here. And I have these smaller, higher frequency things that are my audio components that are up here, right? So it might look something like this. So this is what I've done mathematically is I transform this signal into this signal. They're the same thing. They're both the same signal, but I'm looking at different. It's bringing out different aspects of it, right. I'm mathematically representing this signal in different ways. One is a voltage versus time. And so, for example, even if you look at an audio signal, you'll see the same kind of thing, right? You look at anything that's giving you the representation of your, of the audio of music, right? And you'll see it with all these squiggly lines moving around like this. It's literally just talking about voltage versus time. That's it, right? Or I could talk about voltage versus frequency, right? Frequency is literally the units of frequency are literally 1 over seconds, 1 over time, right? There's a direct mapping between these two. And I can do this direct mapping through something called a Fourier transform to go from time to frequency space and from frequency space back to time space, right? I can go back and forth. There is the same information about the signal encoded in both of these systems, but I'm looking at it in a different space. Now, what's going on here? I am looking at my system in a different space, right? This is a representation of my system in this other space called Wigner space, right? In the same way, this is a frequency space, right? This is just a different space. A space just means I have different mathematical variables, right? So I can vary Q, I can vary P, I can vary beta, I can vary V, and that's why it's a 4-dimensional space, right? Each of these you would have to represent with an axis on a graph. So a 3-dimensional space would look like this. Right. So I'm going from my prior space into this Wigner space, and then, but now these, even though these are interchangeable, right? My frequency, if I go back to here, my frequency time representation that I'm showing here is interchangeable. They're the same information between them, but if I do mathematics on one of these, it's not exact. It doesn't look exactly the same doing mathematics on this versus doing mathematics on this. I have to take whatever operation I'm doing and I have to transform it into the right space, right? I'm looking at seconds here and I'm looking at 1 over seconds here. So I can't, I'm looking at cycles per second versus looking at seconds. So I can't do exactly the same math here and here, or rather, let me take that back. I can do exactly the same math. I can't do it exactly the same way. I have to take the operations that I'm doing in one space and transform them into operations on the other space, right? There is a transformation because there's the same information between each space, but I have to do that transformation from one to the next. So that's what's going on here. If we're saying that in quantum mechanics, I can take this operator. Where'd it go? Oh, no. Right? If I'm saying in quantum mechanics, I can take some function psi, some wave function psi of a particle, and I can find the average, the expected, or the average momentum of that particle doing this operation. That means if instead of psi, I'm using W, right? I've transformed it into W. All right. I will finish this thought and then this will cut it off for today. If I'm going from psi to W, well, I have to change P as well, right? My P hat operator also has to change to be valid in W space and not psi space. So, non-mathematically, what I'm doing is I'm just going from one space into another space. But if I do that, I have to make sure that all of the mathematical operations I'm doing in one space are equivalent to the mathematical operations I'm doing in the other space. It's not just, you can't just do the same thing in both sides, right? So non-mathematically, what I'm doing is I'm dragging everything from one to another. I'm looking, instead of looking at, it's the equivalent of, instead of looking at amplitude versus time, I'm looking at amplitude versus frequency, right? There's that translation between the two that I can do, but I have to do that same translation to all the mathematical operations. Same thing's happening here. The reason why I say it's interesting with the Fourier, it turns out there is a way to apply a Fourier transformation to W to get to another interesting space. And that interesting space has nothing to do with quantum mechanics, which is why that's why I'm doing this, because the fact that this space is analogous to another space means that these operations are analogous to other operations in a different space that might be of interest to electrical engineering instead of quantum physics. And I'm curious as to what the translation is, and if you do that translation, whether you get anything legitimate. The translation itself is going to be legitimate, right? There's a way to do it. Whether that translation gives you any useful information at the end that you didn't have before is an open question, right? And so that's the open question I'm interested in asking at the end of the day. But to get there, we have to understand how to do all of these things. We still haven't gotten to the path integral, right? This is going to be essentially a path integral. We're trying to figure out how to translate path integrals into W space. That's what we're doing, right? We're trying to go from this A into a path integral for W. So that is where I'm going to end things for today. Um, yes. So for the mathematically less inclined, what we're trying to do is we're trying to figure out how to do this translation across different spaces, from 3n p 3n q here to some other space Wigner distribution, right? When we come back on Sunday, we will re-look at all of this, because we are going to have to redo it to understand what the heck is actually going on in any of this. And then we will take our next steps down here, where he's talking about the translation of a partition function into Wigner space. Which what we'll see is a whole lot of patterns. We'll see this plus over 2 and minus over 2, and we're integrating over that variable, right? This is our translation piece. We're going to start seeing these similar patterns crop up, and that'll help us get a little bit of understanding of what's going on, right? We can start leveraging those patterns to start finding connections between these things, and ultimately that's what we'll do. Right. So I apologize. This has been an extremely math-heavy version of Sunday morning papers. Our last Sunday morning papers was a philosophy paper. So if you came back looking for another philosophy paper, I apologize. I will, if I manage to finish the slides I'm trying to finish up today, I will actually put out a real schedule. That is the goal, is to have a more consistent schedule. I might be moving around the schedule a little bit. The problem is right now, my evening Tuesday overlaps with a Toasty stream, and I don't want to do that. And then I was looking at potentially moving the Thursday to the evening. That would be overlapping both of Toasty streams, and I certainly don't want to do that. So I need to figure out better timing for the streams, is what I'm saying. What that will look like, I don't know yet. Well, I appreciate it. I really appreciate you coming in here and listening to me just sit here and blab stupid things. I'll give you a hint. I don't get the math yet either. Like, I have vague sort of wavings in my head as to what some of the math is supposed to be doing, but yeah. So for me, applying it to like the radar, that radar analogy makes more sense, right, in my head, because I've worked with that more often. So the hope is, as I go through the math, right, here's, I guess, for someone who's coming to this without the math background, I hope there's enough other stuff going on that you can conceptually at least sort of follow some of the pathways or some of the thought processes that go on. You might not follow all of the way through, but understand some of the thought processes in a way that's interesting. And at the same time, at least be exposed to some of this math and run into, it might be familiar to you later. What I would like to do at some point, actually, what would be really interesting, I'd like to try doing like a math instructional stream. Maybe we'll do that sometime. That could be a lot of fun. Have everyone come to me with what is the deepest, darkest math that you never understood, and we'll see if we can understand it together. That might be fun, right? Oh yeah, I could. Oh, that's a good idea. I could come up with with like a poll, right? Hey, everyone, send me in the one math thing that you never understood that you always wanted to understand, or physics thing, and we'll try and understand it together. That's a good way for me to put myself in trouble. It'll be a lot of fun. That's a good idea. I like that idea. I'm gonna write that idea down. Uh, I'm trying to get experience with teaching things so that once I actually start teaching, I'll be able to at least sort of do okay. Oh, that is a very restrictive um or a very specific category, but I will take it. Um, at any rate, okay. With that shenanigans out of the way, yes, more to come later. Hopefully an actual schedule will come out today. Fingers crossed. I'm gonna, like I said, I'm gonna try and figure out what the schedule is gonna be. In the meantime, yeah, no worries. Ask away. Fecal teacher. Well, thank you. I appreciate it, Gothic. I'm actually gonna. I remembered this time. I'm gonna look for someone to um to raid. I remembered. Haha. All right. Let's see. Let's go to here. Browse and look. Let's look for science and technology. Let's see who else is streaming. Is there anyone doing anything interesting? There's a bunch of people doing stuff in French. That's not very helpful for most people. We have a whole bunch of you know what? You know what? This guy's doing oh, cool. All right. Well, he was doing a stream from the ISS, but apparently that is not functional right now. Have a good one. Oh, here we go. Is a German radio telescope looking for asteroid. Beautiful. It's in German and everything. I love it. So we're gonna raid them. Why? Because why not? Start the raid. So enjoy staring at a frequency time plot. That's what it looks like. Maybe an amplitude time plot. Anyway, enjoy the radar stream. I will see you guys on Tuesday. On Tuesday. Bye. Happy Mother's Day. Happy Mother's Day. Bye. Yes.